Hi, this is Mark Weissman. Welcome back to my YouTube channel, Wanna Be a Theoretical Physicist. Today I would like to continue my video blogging on quantum field theory. This is my fourth lecture, and we're going to do a long calculation. It's going to be a pretty involved. So this is the QFT log on 12/21/2022, and it's going to be on Colemans calculation of the renormalized self-energy, photon self-energy. So an old but excellent book, Advanced Quantum Mechanics. And don't confuse this with his other book, which is Modern Quantum Mechanics by J.J. Sakurai. He states on page 275, quote, "It is not difficult to convince oneself that almost any quote honest calculation gives D equals 0. This is related to the photon self-energy, referring to the calculation of the photon self-energy. And he goes on, Sakurai, he goes on to mention Pauli Villas and via various other attempts. So this was before dimensional regularization, but probably Sakurai would have had the same thinking on dimensional regularization as well, that these aren't really honest calculations. But in this video, I will discuss Coleman's view and various problems calculating the vacuum polarization So I misspelled this. I always misspell the word vacuum. I don't know why. I'm the world's worst speller. I knew I misspelled it, but the vacuum polarization, and he discusses some of the history on page 715 of his massive QFT lecture book. And this is also discussed by this history. See, there were a lot of problems in the 40s and the 30s, and then Schwinger and Feynman made breakthroughs, but they really also kind of fudged a little bit. And so Coleman kind of says, and I'll quote him, this history is also discussed in Schweber's book, QED, really good book to read, and The Men Who Made It. So Coleman says the trouble was that neither Feynman or Schwinger were using gauge independent cutoffs. But Pauli and Vilas, they developed a technique. They clarified by their realization that we could systematically introduce a cutoff procedure in a gauge invariant way, and then explicitly and unambiguously compute the photon self-energy to show it is zero. And before that, he said something describing this technique. He said, it may be crazy, comma, but it preserves both Lorentz invariance and gauge invariance. So, whether you consider whether this is really an honest calculation. You know, by, let's say, Sakurai standards or the student's standards. It is, of course, up to you. Now, the more popular method today to handle these problems is dimensional regularization. And I think in the next video, I'll do a similar calculation to the one in this video, do it using dimensional regularization. But from what I understand, and I'm far from, I'm just a beginner in these techniques, apparently no technique works all the time. Sometimes you have to use Pauli-Villers, sometimes you have to use dimensional regularization, and there are other techniques, but I don't think everything works all the time. So keep that in mind. So I'm going to outline the calculation that Coleman gives in this video in problem 18.1 of the renormalized Photon. I don't want to go through the whole renormalization procedure that Coleman uses and everything, but when he has a prime on a quantity, he's usually dealing with renormalized fields, and without the prime, he's not. But with the order we're going to calculate to it, it doesn't really matter. And he calls this, and this is sort of like standard notation, though. This is sort of like standard notation, except that sometimes the constant factors, the i's and everything, are different. But he calls it pi tilde prime u nu k squared. And this is on pages 725-729 of Coleman QFT lectures. Okay, so as I said, I'm going to try and go through this as fast as I can. It's a long calculation. I'm not going to show every intermediate step, but I'll show a lot of them. So we have to lowest non-trivial order. We have two diagrams. One's not really a diagram, but anyway. So we're going to define what we're going to try and calculate. First, we have this diagram, which is not renormalized. And this is just equal to a photon coming in, an electron, positron loop. I didn't do that well. I'm terrible at drawing these Feynman diagrams. A photon going out. Coleman always has his diagrams going from right to left, which nobody else does. But it has an advantage that matrix elements also go in quantum mechanics from right to left. This is the initial state, the operator, and the final state. And his diagrams are also the same way. So he has a photon coming in. Let's label it by mu, nu. Momentum is k, going this way, k going this way, and then we have an electron loop, fermion loop. This is p plus k, This is P. And in addition to this diagram, we have the counter term diagram, and this will be defined as minus IE. Sorry about that. So this is the counter term, and it will turn out that this is this counter term goes into the Lagrangian. It's going to represent the term that corrects the what they call wave function, photon wave function, or just field renormalization. So the definition is that minus I tilde prime u nu, the renormalized photon self-energy, is minus I pi tilde mu nu k squared minus I e g mu nu k squared minus k mu k nu. And we choose the constant e to cancel divergences at certain orders. We'll see how that works. So this diagram over here, let's write down using the usual Feynman rules. We get so this minus comes from a fermion loop. This minus IE is the usual interaction vertex with the gamma matrices, which I factored out to minus IE squared. Then I have the integral d4p over 2 pi to the fourth, standard relativistic measure. We have a loop of fermions, so we have to take the trace. And then we have gamma mu I p slash plus k slash plus m over p plus k squared minus m squared plus I epsilon. Gamma nu, this is the propagator for the top half of the loop. And then, then gamma nu I p slash plus m over p squared minus m squared plus I epsilon. Okay. Now the first thing we do is substitute Q equal P plus 1/2 K. This makes the denominator even in Q. And then, so linear terms in Q in the numerator integrate to 0, and we can discard them. So now we get, after doing this substitution, I'm kind of assuming that anybody watching this video at this point in time, if they're still watching, sort of knows how to do Feynman diagrams. So I didn't really define the usual, like Q slash, anything slash is equal to gamma mu Q mu. You know, if you're not familiar with the Feynman slash notation, you will become very soon. So what we're going to do now is we're going to work on the numerator. And discard terms linear in Q, because the denominator, as you can see, is even. If you go in the denominator, these two terms will just go into one another if you go Q to minus Q. And so now we get minus I wait a minute. I already did that. I'm sorry. Let me just erase this. It's a mystery to me. Every time I touch something on the iPad. Okay. So let me start again. Working on the numerator. Discard terms linear in Q and terms with an odd number of gamma matrices, since the trace of an odd number of gammas equals 0. So the numerator, call it n, is equal to the trace gamma u q slash gamma nu q slash minus 1/4 trace gamma u k slash gamma nu k slash plus m squared trace gamma mu gamma nu. Now, using the standard trace identities, you remember, you multiply you dot product the first with the second, and the third with the fourth, and then subtract the first with the dot products, second, fourth, and add the first. So I'm sure you've all done this many times if you've ever seen a Feynman diagram. So this ends up being 4 G mu nu m squared minus q squared plus 1/4 k squared plus 8 q mu q nu minus 1/4 k mu k nu. And so I'll just rewrite once again. Is equal to minus e squared, the integral of D4Q I often, sometimes students in some of the MIT online quantum mechanics classes, they ask about QFT and everything. And I often tell them that QFT is about an order of magnitude more difficult than quantum mechanics. When I say that, I mean not that conceptually it's that much more difficult, it's probably even less difficult, but the calculations that you do, all these manipulations and technology and technical things that you have to develop. Why? I don't understand what's going on. It did it to me again. This is like again. My iPad is just, I don't know what's going on. Sorry about that. So let me see what it erased this time. I have N. Okay, so we can substitute N in here. I'm not going to even write that out. Now we use the usual Feynman parameterization. One over AB equals the integral. So anyway, what I was saying was that quantum field theory is like an order of magnitude more difficult because of all these tricks that people like Feynman and Schwinger and others that you have to master to do these calculations. And it's just math, but it's, you know, it's four-dimensional, Lorentz invariant, gauge covariant, and a lot of hocus pocus, as well, as Feynman would say in the renormalization program. So this is a standard identity that Feynman came up with, and we're going to use it for A equals Q plus 1/2 K squared minus M squared plus I epsilon, and B equal Q minus 1/2 K squared minus M squared plus I epsilon. We're just using these denominators down there. The trick is to combine denominators. So doing this, I get minus I pi tilde mu nu K squared is equal to minus E squared, the integral from 0 to 1 dx, the integral d4q 2 pi to the 4th 4 g mu nu M squared minus Q squared plus 1/4 K squared plus 8 Q mu Q nu minus 1/4 K mu K nu. Divide all this by Q squared plus 2x minus 1/2 Q dot K plus 1/4 K squared minus M squared plus I epsilon squared. Now we want to get rid of this cross term here. So we make one more substitution. Q goes to Q plus X minus 1/2 K. And again, we will drop linear terms. So now we get minus I pi tilde mu nu k squared equal minus 4e squared Okay, we're about halfway there. Bear with me. So, using a standard trick of a Lorentz symmetry, Q nu goes to 1/4 Q squared G mu nu. This is the same thing like you would do in quantum mechanics if you had like Ri, Rj, and you were somehow integrating that, you would end up turning it to like the integral of 1/3 R squared. So same trick. And so finally we get minus I pi tilde mu nu k squared is equal to minus 4e squared. Just going to write it down as a function. It's a function of q, x, k, and m squared. And this function is just what we wrote above. Okay, so we can see just by looking at this integral that as q goes to infinity, f mu nu goes to minus 1/2 g mu nu over q squared plus some other terms over q to the 4th plus terms of order q to the minus 6. Now, we're integrating d4q, so that's like q cubed. So we can see that, or actually, when we finish the integral, it's like q to the 4th. So we end up getting a q squared divergence, a 1 over q divergence, and convergent. This will be convergent. This will lead to a logarithmic divergence, and this is a quadratic divergence. And so what we do with Pauli-Villers is we introduce, in this particular case, 3 heavy masses that we will eventually take to infinity and will decouple from the theory. So that our formula, this is the regularization. The idea of regularization is just to make everything finite. So the idea is if we introduce heavy masses, 3 others, it all leads to the same diagram, the same calculation, except now the parameter will be mi squared instead of m squared, and we'll have a certain coefficient. Now, to eliminate the divergences, we have to satisfy, the coefficients have to satisfy these equations. Now, I don't want to go over the derivation of these equations because they're in my previous video. So we can satisfy these, and Coleman chooses because so we'll have B1 and B3 are -1, so we got a -2, and B2 is 1, so that cancels that. And then we just have, we just have to choose our masses, so that m squared minus m1 squared plus m2 squared minus m3 squared equals 0. So what we're doing is we're choosing these 3 masses to satisfy this, but they have like different statistics. One of them has like they're like ghost masses, but they have different. One is a boson and one is a fermion. We treat the signs differently, but it doesn't seem legitimate, but it works. Okay, so when we do this, the integrand, it goes as order q to the -6, and the integral is convergent. And that's the whole idea. Coleman earlier in the book developed some standard formulas. You may recognize these from the usual dimensional regularization. They're all written a little bit differently. Now from these two formulas, you can easily get this third formula. I wonder if I'm writing these formulas down because I just want to check in the book that I've written them right. Yeah, I think I this is a pi squared, pi squared, pi squared. Yeah, okay, that's good. So from these two, you can easily get this one. Now these dots, these are divergent terms. That cancel when you subtract these and everything, so you don't have to worry about the divergent terms. So we end up getting now the integral, if we do the Q integral in our self-energy formula, we end up getting and the beauty of this is that it's transverse. This is what transverse means. Anybody, for those who have studied QED and photons and electromagnetism, you'll recognize that this is transverse. If you multiply K mu, I'll even explicitly show it. If you multiply K mu times G mu nu K squared minus K mu K nu, you end up getting K nu K squared minus I guess I did that wrong. This should be K nu K squared minus K mu is K squared, which equals 0. So that's what we mean by transverse. And so now our whole thing with the Pauli-Villers regulators, including everything, minus IE squared, 2 pi squared, so we've done the Q integral. Now what you see is we have 3 extra terms. 1 goes in the numerator and 2 go in the denominator. That's why this whole thing with extra signs works out. The m2 squared ends up in the numerator, and the 2 terms in the denominator. As you'll see when we take the limit, this is what it's all about. And now to this we add the counter term for minus IE. I just want to remind you we have our counter term. And this comes from the Lagrangian. So there's no need for a gauge breaking photon mass term. That would be like m gamma a mu. Okay, to renormalize the self energy. Now, if we choose E, then our renormalized self energy becomes see if I can squeeze this in. It's just what we had before, but now we're adding in the products of the squares of the masses. 2 in the denominator, from here, 2 in the numerator and 2 in the denominator. Now we take the limits. And we get so this is finite, transverse, and earlier Coleman had established the basic renormalization conditions. which were minus I pi tilde prime u nu equals I g mu nu k squared minus k mu k nu times the transverse part k squared, and we also had to satisfy pi tilde prime t k squared evaluated at k squared equals 0. And to the order we calculated, if we take the limit as k squared go to 0, we get now this goes to 0 because we're sort of like in the complex plane, but we're at on the positive axis. So whether we're just below or just above doesn't really matter. Either way, epsilon goes to 0 plus, so we're actually just below it, and the ln of 1 equals 0. So I wanted to do one long calculation and just to show you this, and in the next video I'm going to do the dimensional regularization version of this, but not on the same problem, but for scalar electromagnetism, and show how that works, and it works. And so I'll see you next time. Bye bye.